Okay, this is Project Test One's, our second video, questions 11 through 20. Publishers of a magazine wish to determine what proportion of the magazine's 50,000 subscribers are pleased with their subscription. The publishers intend to mail a survey to 1,000 subscribers randomly selected from those who have received the magazine for 5 years. So we have random selection, and that's great. We're taking it for 5 years or more, which may be a problem. And this introduces selection bias, since long subscribing customers are more likely to be pleased with their subscription. Which of the following would best eliminate selection bias? So basically, they're biased because they're taking those who've had it for the longest period of time. If you really want a good sample that's non-biased, you want to represent the entire population, which means you want those who've only had it for a day all the way to those who've had it for as long as the magazine is the longest subscribers possible. So you want to represent every single category, and you'd like to do so proportionally. So let's see what we have. Mail surveys to 2,000 subscribers. Well, that's nice because they increase the sample size. We kind of like that. That's a good thing. Randomly selected, good, from those who've received a magazine for 5 years or more. Once again, we still have the problem that we didn't represent everybody. We only represented those 5 years or more. That's why that's a problem. That's the same problem we initially had. Next one, mail surveys to 1,000 subscribers randomly selected from those who received the magazine for 1 year or less. Well, obviously, if we did that, we didn't get those who had it for more than 1 year, so we didn't represent all those who get the magazine, so that's a bias sample as well. Mail surveys to 1,000 subscribers randomly selected from all subscribers. Hey, if I'm randomly selecting from all subscribers, this is good. This is a good sample. This is probably going to be my answer, but we're going to keep going just in case. We always need to look to see if there's one better. Mail subscribers to 1,000 subscribers randomly selected from those who received the magazine for 5 years or more. And 1,000 subscribers randomly selected from those who received the magazine for 1 year or less. Well, this sounds pretty good too, because I've actually increased my sample size. But notice I only have 0 to 1, and then I have 5 or more. So I don't have anything in the 1 to 5 category, so I didn't represent everybody. So I didn't do a very good stratified sample because I didn't represent every group. Those who are just recently started and the older subscribers, but we don't have any of the middle group. So this is a bad sample. Mail surveys to 500 subscribers randomly selected from a group who have received a free 6-month subscription within the past year. Well, obviously, this is a biased group because they just got a free 6-month subscription. That's different. That doesn't represent all subscribers. Once again, good samples represent the entire population. The only one that does this is letter C. All right, moving on to question number 12. An environmental scientist wants to test the null hypothesis that an anti-pollution device requires is not effective. Under which of the following would a type 1 error be committed? So first off, what was our null hypothesis? Not effective. Well, if that's my null, then my alternative is effective. All right, then it is effective. Now, type 1. We reject, but that's an error. So in this case, to be a type 1, I need to say, hey, you know what? We rejected this and we believe this. So this is what we believed. So we believed that it was effective, but it was an error. So let's work this out. The scientists conclude the anti-pollution device is effective when it's actually not. That sounds pretty good. They believe this, but this was actually true. All right. They rejected this, so they believed this when this was actually true. So that sounds like that's going to be my answer. Letter B, the scientist concludes that anti-pollution device is not effective. No, they concluded that it was effective, so that's false. The scientist concludes the anti-pollution device is effective when it actually is. Concluding that it's effective when it actually is, there's no error there. So this doesn't have an error. An error would be concluding that it is effective when it wasn't, so that's not wrong. This is, hey, we conclude it's effective when it actually is. No error. The scientist concludes the anti-pollution device is not effective when it's not. Once again, no error. A type 1 error cannot be committed in this situation. Anytime you reject, you may have committed a type 1 error. So, excuse me, I marked that out. It's the answer to number 12 is letter A. The scientists believe that it's effective when in fact it was not. We rejected the null and believed the alternative. So please remember, type 1. Reject the null, believe the alternative, and it's an error. You made a mistake, all right? You made a mistake and rejected the null and believed the alternative. Okay, number 13. A data set of test scores is being transformed by applying the following rule to each of the raw scores. Transform score equals this. Which of the following is not true? All right, so the mean of transformed scores equals 3.5 times the mean of the raw score plus 6.2. Well, here what they're testing is whether you can multiply and add constants. So let's talk about that real quickly. So measures of center. With measures of center, you can multiply and add. Measures of center, you can multiply and add. Measures of spread, you can multiply. So you can times, but you cannot add. But cannot add. All right? So, and remember the mean is a measure of center, so we can definitely multiply and we can definitely add. That's true. So this is true, and we're looking for not true. The median transform score, median, that's a measure of center. We can multiply and add. That's true, because it's a measure of center, we can multiply and add. The range of this transform score, we can multiply, but we cannot add because range is a measure of spread. So we can't have this part, so this is false. So letter C will be our answer. All right, now let's continue on for just a moment. The standard deviation of the transform scores is 3.5, and notice they dropped off the 6.2. Why? You can't add, and since they didn't include the plus, this is true. If they'd had the plus 6.2, that would have been false. And then they have the IQR. The IQR, the transform scores is 3.5. And IQR is a measure of spread, Q3 minus Q1, the interquartile range. If they'd had a plus 6.2, this would have been wrong, but they don't, so this is also true. Because you can multiply measures of spread, you just can't add them. The problem with this one is they tried to add a constant, and you cannot add a constant to measure the spread. So the answer to number 13 is C. Number 14, in a random sample of 25 households from the Mountain View School District were surveyed in this survey, data were collected of the age of the youngest child living in each household. The histogram below displays the data collected in the survey. In which of the following intervals is the median of these data located. Well, so the median is the middlemost value. So 25 divided by 2 is 12.5. So better, I'm looking for 12.5. Where is 12.5 located? Well, 4, add 1 to it. Now we're up to 5. Add 2 more. So 4 plus 1 is 5. Add another 2. We're at to 7. Add another 2. Another 5. And now we're up to 12. But I need to get up to 12.5. So I haven't got there yet. So I add 3 more. And this takes me, as soon as I cross that threshold of 12.5, I have enough. So in this case, letter D, 8 to 10-year-olds, all right, and this is number 14, letter D is 8 to 10-year-olds. This group is where I crossed over. 4 plus 1 is 5, plus 2 more is 7, plus 5 more is 12. We needed to get to 12.5. 12 is not enough. Over here, it's like, oh, we're over, but it's the first time we've crossed over the threshold. So for number 14, D is our answer. Number 15, based on a random sample of 50 students, the 90% confidence interval for the mean amount of money students spend on a lunch at a certain high school is found to be within this range. Which of the following statements is true? Well, first off, it's a confidence interval. So what can we say? We can say in repeated sampling, we expect to capture this 90% of the time, or we are 95% or 90% confident that the true population mean lies within the interval. So please remember, we're always talking about the population mean. And those are the two comments we can make. 90% of the time, the mean amount of money that students spend at this school will be between this and this. We don't know if we have a correct interval. There's a 10% chance this is wrong, so we can't say that this is going to be 90% of the time. We're 90% confident that it lies within here, but there's a 10% chance that we're completely wrong and this is not going to work. 90% of all students, well, we can't say that. We have no confidence in we can say 90% of the time, we are 90% confident that it lies within this interval, or if we did this process over and over again, 90% of the time it works, but we can't say that it lies within our endpoints. There's no confidence there. 90% of all random samples, of all random samples. When I say of all random samples, this could be, that's another way of saying in repeated sampling. So in repeated sampling, 50 students obtained would result in sample mean that lies within this. No, because there's a 10% chance that it doesn't do this. So this is also not true. 90% of all random samples of 50 students into this high school would result in a 90% confidence interval that contains a true mean. Oh, if we did this over and over again, in other words, in all random samples, if we did this over and over again, 90% of them would contain the true mean. And that's absolutely the case. You do it over and over again, it's going to work 90% of the time. All right. 10% of all Dynamite mints candies are orange, and 45% of all holiday mint candies are orange. 2 independent random samples, each a size 25, are selected. One from Dynamite mint candies and the other from holiday mint candies. The total number of orange candies in the 2 samples is observed. What is the expected number? So we're looking for expected number and standard deviation for the total number of orange candies. Well, since we have a probability and a fixed number, then I'm thinking this is kind of like a binomial. And so my expected value is going to be NP. So let's do it for the first one. So the first one, we had a sample of 25, and they say 10%. So 25 times 0.10 equals 2.5. For the next one, we also have an expected value of, or we have a sample size of 25 and a probability of 0.45. So 25 times 0.45 is 11.25. Well, it turns out I can add means directly. So I can add these up and I end up getting 11.25 plus 2.5 is 13.75. So my expected value is 13.75. That gets rid of these two. We know it's going to be one of these three. So now I need to think about standard deviation. But my standard deviation for something like this is going to be the square root of NPQ. All right. So in this case, and I'm going to do this down here where I have a little bit more room. We're going to have the square root of 25 times 0.10 times 0.90. And so this would be the dynamite candies. And let's go ahead and calculate that. 25 times 0.1 times 0.9. And I'm going to take the square root of that. And I end up getting 1.5. All right. So this is the square root for dynamite candies. And then I'm going to do the same thing for the holiday candies. And we have 25 times 0.45 times 0.55. And I'll go ahead and calculate that. 25 times 0.45 times 0.55 is 6.1875. Oh, excuse me, I need to take the square, I did not take the square root of that. I need to take the square root of that. And I get 2.487. Now, our initial inclination is to add them. But if you remember, we can't add standard deviations directly. We have to square them and then come back and take the square root of them. So hopefully this will all work out the way it's supposed to. So we're going to go, I'm going to square that 2.487 plus the 1.5 squared. Then I'll take the square root of that. And I end up getting 2.905. So this is my answer. So essentially what all I did is I took 1.5 squared plus 2.487 squared. And then I came back and I had to take the square root of that, 2.905. Okay. All right. So our answer for the 16 is D. Number 17, in a random sample of 60 shoppers chosen from the shoppers at a large shopping mall, 36 indicated that they'd been to a movie in the past month. So we have a sample of 60 and 36. So we have 36 out of 60. In an independent random sample of 50 shoppers, wait a second, chosen from the shoppers at a large downtown mall, downtown shopping area, 31 had indicated they'd been to a movie in the last month. So we have two samples. We have a sample of 60 and we have a sample of 50. So we have two independent random samples. That's important. All right. What significance tests should be used to determine whether these data provide sufficient evidence to reject the hypothesis that the proportion? All right, we have two samples. So this is going to be a two sample proportion test. I know this because I have two samples, two independent random samples, and they just told me it was a proportion. Now, all proportion tests are z-test. So if the proportion test, it's a z-test. So one proportion z-test, nope. One, no, one. Two proportion z-test. All right, so number 17 is D. Okay, number 18 and 19, I'm gonna have a little bit of trouble on because we have the large table. So I'm gonna do the best I can in this. So we have this large table In the 1830s, land surveyors began to survey the land acquired in the Louisiana Purchase. Part of their task was to note the sizes of trees they encountered in the survey. The table of data below is for bur oak trees measured during the survey. So we have a frequency, a relative frequency, a cumulative frequency, and the cumulative relative frequency. So let's talk about these. All right. We had two trees that were 4 inches in diameter, and out of the total number of trees, that amounted to this percent. Okay, so that's going to be the cumulative right there. Here, we have 5 trees, and that represented this percent of the trees. Well, 2 plus 5 is 7, 7 over the total number of trees. And by the way, they tell us at the very bottom that they had 1,000 trees. All right, they had 1,000 trees. So 7 out of 1,000 is this, etc. And that's how they went about doing, not 7, they had, so I misspoke. They had 431 trees. That's 100%. That's the 100%. This is a percent, a running percent total. This is 431. So let's just real quickly look at this. Let's try 26 over 431 and just see what happens. 26 divided by 431 equals about 6%. And that's what they have right there. So basically, this is just 2 plus 5 is 7. 2 plus 5 plus 19 is 26. All right. And this is all divided by 431. And these are also all divided by 431, but it's 2 divided by 431, 5 divided by 431. This is just the running total divided by 431. So confusing little table there. And so number 18, which of the following differences in cumulative relative frequencies given the proportion of trees that are 12 inches to 6 inches inclusive in the diameter? So we want 12 to 16 inches inclusive. All right. Now let's look at this table real quickly. 16-inch trees goes to here. So that's 72.6%. So 0.726. But then I need to subtract out what I don't want. And it says we want 12 to 16. So we want to include 12. So I'm going to subtract out everything I don't want, which is below this line here. So I'm going to subtract out 0.325. And that makes letter C my answer. Okay, so I wanted all the way up. 72% of the trees were 16 inches or less. Then I'm going to subtract out what I don't want because I want the 12-inch trees. So I subtract out everything I don't want, which is this part right here. Okay, all right. Number 19, an outlier may be defined as a data point that is more than 1.5 times the interquartile range below the lower quartile, or more than 1.5 times the interquartile range above the upper quartile range. According to this definition, what is a diameter in inches of the smallest tree that is an outlier? So first off, we are going to need to calculate our IQR. So IQR equals Q3 minus Q1. So Q3 is at the 75th percentile and Q1 is at the 25th percentile. So I need to look up and find these values on the table. So as I go up on the table, I'm going to go all the way up and look for the 75th percentile. So 72.6%, 73%, not high enough. So my 75th percentile, 75% of the trees are 18 inches or less. All right. So 75% of the trees are 18 inches or less. You're like, well, wait a second, that's 84%, that's too big. And I'm like, I have to go to the highest value, the first highest value that includes 75%. 73 did not include it, or 72 didn't include it, 73 didn't include it. Oh, here's the first one that includes it. So I have to take 18. So 18 is my Q3 value. That is my highest value. That is my 75th percentile, 18-inch trees. Now I need to find the 25th percentile. Well, this is 16%, not big enough, 19%. So these aren't big enough. That's not big enough. All of a sudden, I'm at 31%, but this is the first time I've got to 25%. So this is the first time I've gotten to 25%. So this is my value. So 10-inch trees are my Q1. 10-inch trees are Q1. So my IQR happens to be 8. 18 minus 10. Well, our fences, let's write our fence formula. Our fence formulas, and we have two fence formulas. X has to be less than Q1 minus 1.5 IQR. And X has to be greater than Q3 plus 1.5 IQR. Well, what was our Q1 value? We said our Q1 value was 10. So 10 minus 1.5 times 8. 10 minus, and this becomes 12, and we end up X has to be less than -2. Well, that's a problem. There's no -2 tree. So we don't have any outliers on the upper side. I mean, on the lower side. So no outliers on the lower side. Let's try the upper side. Well, Q3 is 18. So 18 plus 1.5 times 8. So 18 plus 1.5 times 8 is 12. So X has to be greater than 30. So let's go back and look at our table and see where that occurs at. All right, see where that occurs at. So X has to be greater than 30. And so I go, okay, here's 30. All right, there's my 30-inch tree. And it's like, oh, wait a second. It has to be greater. It can't be 30. 30 is on the fence. 30 is on the fence, so I need a 31. There is no 31. There's no 32. There's no 33. So the first one that's an outlier is at 34. Now, had there been a 31, it'd be an outlier. Had there been a 32, it would have been an outlier. But 30 is on the fence, and on the fence is not an outlier. And they tried to trick you because they included 30. But the first one that's not an outlier occurs at 34. That table is a particularly challenging, those two problems are particularly challenging. All right, last problem for this video, number 20. The National Honor Society at Central High School plans to a random sample group of 100 seniors from all high schools in the state in which Central High School is located to determine the average number of hours per week spent on homework. A 95% confidence interval for the mean number of hours spent on homework will then be constructed using the sample data. Before selecting the data, the National Honor Society decides it wants to decrease the margin of error. Which of the following is the best way to decrease the margin of error? And they're looking for determine the average number. So we are going to be working with a mean. So this is our formula for a mean: X bar plus or minus T star S divided by square root of N. Please remember, this part right here is the margin of error. Anything we're multiplying by increases it. Anything we're dividing by decreases it. So we want to decrease the margin of error. So if I'm multiplying, I need to drop my T star, which means my confidence level. If I want to decrease, confidence level goes down, then margin of error goes down. If my standard deviation goes down because I'm multiplying, then my margin of error goes down. So if I can decrease the standard of error, which I probably can't because it came from the sample. If I increase my sample size, because I'm dividing by it, my margin of error goes down. So we want to decrease the margin of error, and probably the best way to do that would be to increase the sample size, right? So number 20, the best answer is D, increase the sample size, because we're dividing, they move in opposite directions. All right, that'll end this video.